Okay, hold on for a moment, please. Okay, we have some difficulties, so we are trying to solve. Okay, I will start again because the streaming was not ready. So, welcome to this oral session, everyone. We have 5 presentations until 1 p.m. Some of them will be in virtual mode and some of them in video presentation mode. So we start with paper 240. The title is Design of Power Quality Virtual Lab Toolbox using LabVIEW Multisim. This is a video presentation and the authors are S. Haidar, E. Moussa, M. El Hassan, M. Badawi, El Najjar. So the video can start.
Hello everyone, my name is Sandra Haidar. I will be presenting a project titled Design of Power Quality Virtual Lab Toolbox using LabVIEW and Multisim. From that, what is power quality? Power quality is defined as a set of electrical boundaries that allows equipment to function in its intended manner without significant loss of performance or life expectancy. Power quality is a major concern in the electric power industry, as its main goal is to free the system from disturbances and obtaining good performance results in the production cycle. All electrical devices in which power electronics and nonlinear loads are integrated are considered sensitive to power quality disturbances such as electric motors, computers, generators, transformers, or household appliances. Thus, quality loss is a main feature that can determine the severity of an economic loss caused by any disturbance in power systems. As power quality problems are arising, the knowledge in power quality became a must for electrical engineers. The Power Quality Virtual Lab will be used by electrical engineers to enhance their knowledge and awareness on power quality disturbances in according to power quality standards. This lab will point up all kinds of distortions and their effects on power quality indices. It presents itself as a feasible, eco-friendly, and accessible learning tool, as it doesn't require any equipment or electrical components to use. Also, it doesn't require the usage of high voltages, which will make it an efficient, risk-free, and a fast learning experience. This virtual lab is proposed to be a training tool that will help in learning and executing the concepts of power quality. Electrical engineers will become more familiar with major power quality issues and more aware about the problems tackling power systems and nonlinear devices. This virtual lab is built using an LabVIEW and Multisim and is composed out of many simulations and experiments, each with its learning objectives. LabVIEW and Multisim are tools that can be used for acquiring, analyzing, displaying, and storing data. Any circuit built using Multisim can be integrated in the Power Quality Virtual Lab to be analyzed in accordance with the power quality indices. As for the power quality disturbances that a system can be subject to, there are short duration voltage disturbances including voltage sag, voltage swell, and interruption, and also waveform distortion including harmonics and unbalance. Therefore, this is a voltage sag. It is a reduction in the RMS voltage for a short time between 0.08 seconds and 0.16 seconds for less than 90% of the nominal RMS voltage, where the voltage had been decreased from 80 volt to 40 volt. The voltage sag can happen during a starting of a large machine such as the motor. Whereas this is a voltage swell. Unlike the voltage sag, the voltage swell is an increase in the RMS voltage for a short time between 0.08 seconds and 0.16 seconds for more than 110% of the nominal RMS voltage, where the voltage had been increased from 80 volt to around 120 volt. The voltage swell can happen due to losing a large load suddenly. As for the interruption, it is a complete loss of voltage for a small period of time between 0.08 seconds and 0.16 seconds. It can be due to control malfunctions and equipment failures. As for the harmonics, they are present in sinusoidal voltages and currents and appear in all frequencies. However, in the industrial field, the frequencies range between 50 to 60 Hz. They are defined in power systems as a sum of sine wave of different frequencies but multiple of the fundamental frequency. Therefore, a signal containing many harmonic components can be decomposed to more than one signal with different frequencies. A sinusoidal signal loses the proper shape of a sine wave when it becomes distorted with harmonics but remains a periodic signal. The appearance of harmonics is due to the high usage of nonlinear devices and nonlinear loads in power system. As you can see, the harmonics happen between 0.06 seconds and 0.15 seconds. The unbalance is also considered as a power quality disturbance that occurs when having different RMS magnitude of the phases or when the phase angle between each consecutive line is not equal, as it is clear here between 0.04 seconds and 0.15 seconds. The main reason of unbalance is adding loads on a particular phase more than the others. Therefore, many power quality indices affected by these power quality issues are tackled, including the RMS, the RMS voltage, the total harmonic distortion, the distortion index, the crest factor, the displacement power factor, and the true power factor. These power quality indices are crucial in representing, quantifying, and comparing complex power quality phenomena. The implementation of these steps in LabVIEW yield to an interface, and the integration of all these individual components allow the formation of a virtual lab able to showcase the effects of the disturbances on the established power quality indices. So now, as we have all this information, the simulations all attached, the equations and formula all plugged in and designed, what would the electrical engineer see? This is exactly what they will see. The Power Quality Virtual Lab interface will pop up in front of the user to start the process experimenting many power quality disturbances. The electrical engineer can create a voltage sag, a voltage swell, harmonics, interruption, unbalance, and also a combination of more than one disturbance. From the first tab, the electrical engineer would set the voltage peak of the sine wave source, the frequency, and the duration of the signal in their corresponding control blocks. The fundamental waveform will appear in the graph. Here, in the next tab, the user will choose whether the desired change is a sag, a swell, or an interruption. Then we'll set the magnitude of the sag or swell in form of percentage and the start and end time in their corresponding places. It is crucial to mention that the electrical engineer should pay attention in choosing the start and end time of the voltage disturbance within the duration of the signal to actually see the desired change. In the next tab, the user has the option to add harmonics to the system by specifying the order and magnitude of each harmonic component and the duration of the distorted signal. As for the unbalance, it can be created in the Unbalance Control tab by either specifying the phase of unbalanced voltages or by setting the peak voltage of each phase and the desired frequency and duration of the signal. This virtual tool allows the user to choose the type of disturbance they want to investigate, or a combination of disturbances of his choice. In addition, they are able to choose the start and end time of each disturbance separately. Once these steps are accomplished and the model starts running, the results will appear in the next two tabs called, respectively, Obtained Graphs and Power Quality Indices. Many simulations and experiments were prepared to help the electrical engineer enhance their knowledge in power quality and become familiar with major power quality issues and indices. The plot results of the voltage and current, along with the measured parameters, will help the user to come out with the right analysis and interpretation on power quality in terms of indices and problems. For example, two types of disturbances at two different times were simulated using the Virtual Lab toolbox. This figure represents the original waveform where the values of the voltage peak, the frequency, and the duration of the signal were set by the user. This fundamental waveform is free from any disturbance. In the next figure, the push button is set on the sag side. Therefore, a sag voltage of 60% of the nominal voltage tackles the signal between 0.02 seconds and 0.06 seconds. In addition to the sag created, the signal is distorted by three harmonic components of order 3, 5, and 7 with magnitudes of 10 volt, 50 volt, and 75 volt respectively, as shown in this UI screen. These harmonics interfere in the signal between 0.06 seconds and 0.12 seconds. Up to 50 harmonics can appear in a system. However, only 3 harmonics can be added in this virtual tool, as its main purpose is to learn and investigate the basics and measures of power quality. Therefore, the obtained results of the voltage and current signals are shown in this figure, where the plot 1 represents the three-phase voltage source, plot 2 is the single-phase voltage, and plot 3 is the single-phase current. The two disturbances are clearly marked in the first plot. The first rectangle represents a sag voltage that is less than the fundamental voltage. The second rectangle highlights the distorting signal consisting of the fundamental harmonic component along with the three added harmonics. And then, the power quality indices are being measured and analyzed on the implemented system along with the RLC load before any disturbance, during sag, during the harmonic distortion, and after these disturbances. Some of these power quality indices were generated directly through LabVIEW blocks, others were designed using mathematical blocks to perform the right operations. These measures are displayed in the following table to clearly analyze how the parameters are affected by each disturbance. This table indicates that the RMS value is affected by all types of disturbance. When no disturbance occurs, the RMS voltage is almost 70.5 volt. This RMS value decreases in the case of a sag voltage to reach 28.2 volt, and increase in the case of swell voltage or harmonic distortion to reach 95.38 volt. However, THD, TIF, and VT are only affected in the presence of harmonics. Otherwise, they are equal to zero. The harmonic plot in a normal signal only contains the fundamental component, whereas the harmonic plot of a distorted signal shows the fundamental component along with the third, fifth, and seventh order harmonics. In this case, the THD, TIF, and VT will highly increase. The distortion power factor related to the total harmonic distortion is equal to 1 in a signal free of harmonics. Hence, this factor decreases to 0.18 during the presence of harmonic distortion. And while the displacement power factor remains the same even with the presence of harmonics, the true power factor gets smaller as harmonics are added and becomes less than displacement factor. Both TPF and DPF are equal in non-harmonic situations. To sum it,
Thank you very much for your presentation. We open question time. Any question from the audience? Yeah. So we need a microphone, please. I think the author is online using Skype. So we can ask, and I will wait for the answer. So wait for a moment, please, for the microphone. Yes, I think the author is online. Can you confirm, please? Anyway, you can ask.
My question, actually, it's a very nice idea to combine these two softwares together, but I don't know how do they make sure how exact results the virtual lab they have done gives them. Did they compare it to LabVIEW or to Multisim? How do they make sure they get exact results? This is my questions.
Okay, thank you. I don't know if the author can answer online. Is he or she online? Okay, it looks like yes, it's online.
Hello, can you hear me? Hello? Okay. Sorry for technical problems. And I'm Michele Zanoni, a researcher from RSC, Italy. And today my presentation deals with automated tool based on deep learning to assess voltage dips validity. Integration in the Queen medium voltage network monitoring system. So we start to deal with framework and open issue in power quality monitoring system in distribution grid. Then we present the Delphi application, that it is an application developed by my research group, and how this application for voltage dips validity identification is integrating with the QueenPy service and in our database. Then we perform some power quality analysis, and we can go to conclusion. So it is well known that nowadays renewable energy sourcing, distorting law drive the attention in power quality. And in the new smart grid scenario, the importance of power quality monitoring will be increasing in the next year, especially in medium voltage distribution grid. If we think to power quality, we have to refer to standard EN 5160. And today I focus my attention on the voltage dips. What is a voltage dips? Is a temporary reduction of the voltage supply under the 90% of its nominal value. And when we want to when we talk about voltage dips and we want to use it as an index for regulatory purpose, we have to pay attention to origin and especially validity. And today I focus my attention on this point, and the validity of voltage dips. And in this framework, in the last year, the use of advanced signal processing technique and machine learning algorithm can be a possible way to solve this problem. But I start to talk about what is the Queen monitoring system. Since 2006, RSC developed a monitoring system of the Italian medium voltage distribution grid. And we have installed in the primary substation 400 measurement units in the to the low voltage side of the voltage transformer in the primary substation. And in each of these measurement units perform power quality measurement according to standard IC 61440, and they have an additional feature. So we can acquire waveform and RMS sequences during some special events as voltage dips. So data that are collected in this year can be found on our website. And if you want to visit our website, we are happy, of course. So, but what is an open issue? What is the open issue in voltage dips validity? As in the distribution network, Italian distribution network, we know that we have a certain number of isolating natural system topology. So it is well known that faults involving ground produce, of course, a sinusoidal zero sequence that can be that can produce a saturation of the voltage transformer core. So this produces a typical false voltage dip because there is a reduction of the output of the transformer, but there is no reduction in the voltage supply. And that it can be seen because we have a typical distorted waveform with the camel-ups or Dodge's hat, and we have this particular wave in the RMS value. But of course, this voltage dips has to be cleaned up from statistics because there is no a very voltage dips. It's only a saturation of the voltage transformer. So we have to remove these events from our statistics. Of course, this problem was well known since 2006, and our company decided to validate a second harmonic component algorithm. So by evaluating the second harmonic in the output of the voltage transformer, we set a threshold and a minimum number of subsequent overcomings, and through this value, we developed an algorithm in order to classify the voltage dips. So when there is no second harmonic component, we have the true voltage dips, and when the second harmonic overcome the threshold and the minimum number of subsequent overcomings, we have a false voltage dips. But there are some cases where the algorithm failed, and so we have not defined cases because the criterion is not able to give always an answer. And this number of events are not negligible because we have the 12% of annual events. So in the last years, we decided to develop a new criterion based on deep learning techniques. And we developed an application called Delphi, that is deep learning for false voltage dips identification. And we start from input data as RMS voltage values. So we take the data, we generate an image, and then we pass it to the classifier that we developed. And this classifier gives us always a Boolean answer. So we have true, false, and it's capable to catch also true plus false events. So we have a first part of the event that is a true voltage dips, and at the end a false voltage dips. Of course, we test on a small set of data this criterion, and we trained it, of course, and we reached a performance of 95% on a small set of events. But now we have to do the next step. So we have to integrate this algorithm in the Queen system, in our monitoring system. And this is the main topic of this presentation, because we developed a Python language toolbox that is called the Queen PyService that integrates the Queen database that is online now with advanced services. In particular, we are able to read all the voltage dips recorded now and stored in our database. We can generate RMS voltage dip sequences. And of course, we can integrate the deep learning classifier in our database. So now we are able to classify voltage dips recorded in our MySQL database with the new classifier in order to verify if it's able to perform and identify false event. So thanks to this tool, we perform some broad statistical analysis. We decide to collect voltage dips recorded by 61 measurement units from 2015 to 2020. And so we have analyzed nearby 4,000 events. From these statistics, we removed events occurred simultaneously with the tripping of a high voltage line distance protection because they are not of interest in the regulatory purpose because these events has to be attributed to the TSO and not to the DSO. So what kind of statistical analysis we perform? First of all, we do a comparison, basically, between the Queen criterion and the Delphi criterion. So we compare the two different algorithms. And then we perform some metrics, and we evaluate the N2A and the N3B with respect to the measurement point that can be computed with a formula that you can see in the slide. What is the N2A? The N2A is an index that counts the number of voltage dips occurred below the immunity zone for class 2 equipment, and the N3B is the index that counts the number of voltage dips occurred below the immunity zone for class 3 equipment. So first results, these are the results with the Queen criterion, so the second harmonic criterion. So we can see that the trends are quite stable over the years. So we have the 78% of true events and the 12% of false events, and a certain number of not defined events that are not negligible because they are the 11%. When we use the Delphi application, we can see that the number of true events increase up to the 85%, while the false events remain quite stable, equal to 13%, and the true plus false events are equal to 1.8%. But the most important thing that these events that now from not defined events are true events, and so we have to count when we evaluate the matrix, the power quality matrix, are not negligible, because as we can see, if we evaluate the N2A and the N3B by using the true event classified by the Queen criterion, we reach an average value of 32.2 and 14.8, while if you use the true event classified by the Delphi classifier, we have an N2A equal to 40 and an N3B equal to 20.6. So we can see that not defined events by the true criterion are now classified as true by the Delphi classifier. And this contributes to both N2A and N3B. So the matrix increases respectively by the 20% and the 39%. Going to conclusion, today I present the Queen Pi service application. It's a Python tool language that integrates advanced functionality in our monitoring system, that is the Queen system. We integrate the Delphi classifier, that is a deep learning algorithm for false event identification. And for the first time, we validated and tested on a large amount of data, nearby 4,000 events, over a 6-year monitoring campaign on a small set of 61 measurement units. The comparison between the old criterion, so the second harmonic criterion, and the Delphi algorithm tell us that not defined events by the Queen criterion are most classified as true by the Delphi classifier, and those events are not negligible because contribute to boost the N2A and the N3B. So thank you for the attention. I hope that you can hear me, and I'm here for questions. Thank you.
So we are running quite tight on time. So we open a question time. Any question from the audience? Any questions? Well, I have one question. Have you compared your algorithm with any further additional technique?
For now, no, because the first things we have to do is to compare our algorithm that we can use on our database, because the algorithm based on the second harmonic is installed in the measurement unit. So for us, it was easy to compare.
Al final lo tienes o no?
In the next future, we are interested to also have comparison between other algorithms that we are studying in the future. So it will be, of course,
problem. It's not an issue that it was
Okay. Thank you very much. Next presentation. The title of TSO Tenet in Brabant, the Netherlands. I don't know if the speaker is online. The authors are W.L. Brockman, GBM Van Wijs, V. Cook, and GFG Coben. Do we have any presenter online?
I hope you can hear me now. I'm struggling a bit because YouTube is lagging behind Skype, so I hear it double.
Yeah.
Slower. So my name is Vladimir Chuk. I'm an assistant professor at the Eindhoven Technical University of Technology, and I will present this paper in the name of the group. The first author is Willem Broekman. He's a master student in our group, and he did this study as an internship within TenneT, that is the transmission system operator in the Netherlands and a part of Germany. And also together with us, we had Jeroen van Waas, who is part-time at TUE, but most of the time actually working at TenneT, and Professor Chef Coben, who is also leading the power quality research in our group. So I shall begin with the introduction and motivation. Let me try to also use a laser pointer. The aim of this study was to look into the impact of certain system changes on the harmonic voltage levels in the province of North Brabant in the Netherlands. And most of these changes in harmonic levels arise from, for example, capacitor energization or de-energization, then swapping some of the overhead lines for cable connections. That is something that's becoming more and more popular in the recent times and is also going to happen more and more in the future. Then also outages of certain overhead lines, either planned or unplanned. They're also sort of a source of short circuit level reductions, as well as some generation shifts to renewable energy sources. And this was the reason to start studying them and trying to pinpoint some of the sources of changes, and can we actually quantify the level of change that comes due to an event or a change in the system. And we were looking into a method to correlate the logged operational changes to the changes of measured harmonic levels in the system. And the study object, as mentioned, is the 150 kilovolt network in the province of North Brabant, and it is a highly meshed network. I'll show also a schematic in a few slides, which is operated by TenneT. Now, one of the reasons why this study was done, it was not only to quantify these changes, but also to look into an option for model validation in the future. Because, for example, I already mentioned that changing an overhead line to a cable connection can bring some significant changes, and the idea is also to study this with simulations. Now, it's sometimes difficult to say if the simulation is matching reality really well. So the idea is if we can quantify the effect in measurements, then we can also see the relative changes and compare it to a simulation study. And hopefully we can do more model validation in the future based on actual measurements which are present more and more. Now, a few words about the monitoring in the system. First of all, the reason why there is monitoring in the high voltage and extra high voltage systems is that there is a local grid code called netcode electriciteit, which specifies a THD limit for harmonic voltages. But further than only the THD limit, which is the normative one, the TSO also uses IEC 61000-3-6 with its planning levels as an internal objective. And that is used then to control the harmonic levels also on the THD level, looking into planning levels. And these planning levels are something that gets exceeded now and then, and that's a point of attention why the studies are done. Now, presently, already all high voltage and extra high voltage customer connections are equipped with continuous power quality monitoring. There are power quality monitors of different types, but in any case, they are logging the THD and the individual harmonic voltages at a rate of once in 10 minutes, as specified in the measurement standard. And each time that there is an exceedance of the planning level, it's a trigger and a warning sign to look into that further on. Now, to correlate the actual system changes to something that's happening with harmonic levels, further data is used. There is a system called EMS, which is logging all of these type of operations with a timestamp. So to give an example, if a capacitor bank is energized, this is noted with a timestamp in the system. Also, if it is de-energized, but also if a line is energized or de-energized, both due to a fault or planned maintenance, all of these events are logged with a timestamp, and that's something that we wanted to use with the correlations of events and measurements. Now, the methodology used is based on either a Thevenin or a Norton equivalent. If we simplify the system and looking into a change from a perspective of background harmonics and impedance interaction, we can look at this simplified model, which is a Norton model, where we have the system modeled as background harmonic emission, in this case is a current source with a Norton equivalent, and a system impedance. Of course, such a model we built for each harmonic individually. And then there is a connected party where there is a monitor at a point of common coupling where we actually can measure the harmonic voltages. Now, in this model, we neglect the emission of the customer connection, and that's usually also relatively low, but it is an assumption that most of the harmonics actually come from all of the other connectees in the network, and these background harmonic levels are then amplified or damped based on the impedance interaction of the system and the customer connections, and that can be specified in this formula. I will not go into the mathematics for the sake of time, but also because this is already present in the literature. What we focused on was what happens if now there is, for example, a capacitor bank being energized. What happens then is that this impedance of the system equivalent will change slightly or perhaps more, and we will get a new state where the same formula we can rewrite with a new value of the system impedance, and we have then the two states before and after a change, where we actually have something measured, and that's the harmonic voltage at the terminals of a connectee. Now, based on these, we can specify an amplification factor, and that can be either amplification or reduction, which is specified based on the new state measurement and the previous state measurement. And by dividing them, we can define this factor as something to quantify the change in the harmonic level due to a change. Now, we are then focusing on individual changes, so hoping that when a capacitor bank or something else changes its state, there are not much significant changes in the system. So if we can measure the voltage just pre or and after it, in these 10-minute intervals, we quantify the amplification factor, and that's how we quantify the change as well. Now, the moment of actually doing the calculation is done based on this EMS data, where the logged changes are found with Python code, and then this code is used to also extract the measurements from a different system and then calculate these amplification factors. The preference is that we have multiple events. So, for example, a capacitor bank is likely to operate even sometimes multiple times per day. So if we have every time the rising edge and the lowering edge when it is switched on and off, if we follow these amplification factors, hopefully there is a strong correlation that we can actually pinpoint that there is a certain factor or a relatively low range of values of changes happening due to a single event. Now, this is the schematic of this 150 kilovolt network specified with these blue lines. Those are the 150 kV lines. They're always in parallel. It is a mesh network, and it is redundant. In principle, the N-2 redundancy is required in the Netherlands, and it has connections to the 380 kilovolt network. Those are the faded red lines around, with certain connections to these substations. There are two colors here. You can notice some red dots. Those will be the substations without capacitor banks. And then there are further also the yellow dots. Those are substations that do have capacitor banks. Now, the paper itself contains results from multiple of these substations and events. But here, for the sake of time, I will present only the results of the study at substation Marheise, which also has two capacitor banks. And it's also interacting with the substation Schertogenbos Nord, which is quite far away. It's 3 buses away, and some changes are noticed. So I will display the results of these. This is more to have a geographical idea of what we are talking about. Now I will show the results of the case study. There's quite some information, so I will show these graphs one by one. The first graph are measured values for 4 harmonic orders and the THD relative to the planning level of each of those. And it was noticed that there are relatively often exceedances of the 7th harmonic order, and in some rare cases of the 23rd, but that's not something that I will discuss more. I will focus on the 7th harmonic order. And then below, we can see the extracted results of the Python code showing at those intervals also what was happening with capacitor banks. The first 2 are capacitor banks at Marheise. There is a larger one and a smaller one. And then there is also the 3rd one at substation Den Bosch Nord, which is also a significant one. Now, what was noticed is whenever, especially the larger capacitor bank at substation Marheise is switched on, the harmonic voltage level of the 7th order goes up significantly. And when it goes down, we can also see a decrease on multiple points, such as here, for example, and then rising back up when it's going up and going down as well. Now, substation Den Bosch Nord has actually a positive effect. When it is energized, we can see a decrease of harmonic level. Oh, sorry. So this event over here is in line with this decrease over here. And we can see more of these situations happening. Capacitor bank energized, harmonic levels decreasing, and so on. And we pinpointed some intervals too with the larger capacitor bank at substation Marheise, and then 2 with the capacitor bank at Den Bosch Nord. That leads to a decrease, and I will show some amplification factors related to this. It is noticeable that there is a strong correlation, but also there are moments in time when it is not so easy to explain everything. And the results can be traced back also in some simulations. So this is the harmonic impedance at this substation in different contingencies. So it includes also capacitor banks being energized, such as here, impedance versus frequency. but also other system changes, such as, for example, a line being de-energized. And what happens, it's quite complex, and the values are varying quite a bit in the impedance. So if we focus on the 7th harmonic, there can be, for example, a
Please,
30%
you
change
need
due to something else.
finish because we are run out of time. Please, thank you.
Okay, thanks. I will go to conclusions very quickly. So the situation is actually quite complex, and therefore the amplification factors are not always consistent. So we have situations where there is a very small range of amplification factors happening, both an increase and decrease, but also situation when it is a wider range. So to conclude, this analysis gives insights in the results of these events, and we can trace back very strong correlations, and that's good because we can in the future look into model validation, but there are also some more complex cases which could not be studied only based on these events. So we will have to look into more system changes for an actual system validation study. Thank you. That was all for my slides. I'm here for any questions.
Okay, thank you for your presentation. We open a brief question time. Any question from the audience? Yeah, I have one question. The theoretical model put forward by the authors seems to suffer from some shortcomings and weakness in terms of robustness as explained by the authors. Have you considered other more reliable alternatives?
Well, yes, for sure. There are impacts of assumptions that, for example, bring to this problem of a wider range of amplification factors, and that comes due to a few things. For example, not knowing the emission of that customer connection, but also changes in the system. So in principle, what would help is actually trying to extract more data from both the harmonic measurements and the EMS system of system changes. So basically linking more of this data, for example, with a similar Python script could further lead to a situation where we can exclude some moments in time as unreliable, for example, because too much happened at the same time. Or perhaps tell us more about system changes where we could actually, let's say, explain why there is more change in the amplification factor. So yes, that is basically a needed further step.
Okay, thank you very much. We have to go to move on to the next presentation because we are very tight of time. So the next work is the paper 352, Impact of Harmonic Distortion and the Supraharmonic Emission of Pulse with Modulated Single-Phase Power Electronic Devices. The authors are E. Kaufhold, J. Meyer, and P. Schegner from the Institute of Electrical Power System and High Voltage Engineering, Technische Universität of Dresden, Germany. So go ahead, please.
Hello, can you, thank you, can you hear me? There seems to be like, okay, thank you. So I assume you can all hear me. So one word already is Kaufhold, and I'm going to present our paper for the ICRP, which deals basically with the impact of harmonic distortion on the supraharmonic emission, specifically on single-phase power electronic devices. So I'll give a brief introduction, of course, as always, and we will come to the state of the art. We will discuss, of course, the main focus of this paper, which is basically the interaction between harmonic and supraharmonic frequency range. Then I will show some laboratory test measurements that we have performed on available devices. And finally, we will draw the conclusion, of course, of what we have. Okay. There's the presentation is lagging behind. I'm sorry, the slides will come. I'm sorry for the inconvenience, but there seems to be a technical problem at the moment. Okay, now we can go. So we see a growth of power electronic devices in the voltage networks. And this specifically also means that we have an increasing share of single-phase converters and inverters, which are the focus of this study. So where are they present? Well, we can see them in photovoltaic application, storage systems, and also in electric vehicle chargers. And the challenge is that these devices have a non-ideal voltage current characteristic, and generally speaking, for any PE device. So this means it's distortion at the point of connection. The problem is that the impact of the network background distortion will change compared or in relation to other grid-connected devices. So if we connect a lot of PE devices to the low voltage network, other PE devices will see a different and, let's say, even a stronger background distortion, which means that the device operation of each individual device will be challenged. And that can lead to device instabilities and also, in general, just to high current emission. So far, the studies have been performed in different frequency ranges, namely the harmonic frequency range, which is between 50 hertz and 2 kilohertz typically. And as we define it in this study, also the supraharmonic frequency range above 2 kilohertz up to often 150 kilohertz and even above. So this study aims actually to address and understand the frequency coupling between the harmonic and the supraharmonic range. So not study them independently, but actually look at the impact of single-phase inverters and converters on this interaction between the frequency ranges. So just as a brief overview for the state of the art, when we come to modeling approaches, we have 3 different approaches that we can categorize based on the available knowledge, which is basically the white box model that requires a lot of detailed knowledge. Basically, we have to know all internal parameters and the structure. So we can present this device in a high degree of detail. And this leads to a high implementation effort. And of course, when we perform such studies, also a high computational effort. Secondly, we have the gray box approach. This has not gained a lot of attraction so far, but would include partial knowledge. Let's say if we know partial components of the device, and we can include them in, let's say, an equivalent circuit model, for example. The last one is the black box approach when it comes to unknown model topologies and parameters, which requires measurement-based approaches because we have only generic knowledge about the individual devices, and then we can perform impedance-based studies. So these devices, it requires a lot of background knowledge. And one effect of these devices is the frequency coupling. Frequency coupling means basically that if we apply a certain voltage frequency component at the device clamps, then we get a current frequency at another frequency. So basically, we can relate one frequency in the voltage to other frequencies in the current. And we can derive a so-called frequency coupling matrix that represents the specific device behavior by relating a reference current and a reference voltage to a different distortion in the applied voltage, and then calculating the resulting current in terms of an admittance matrix, which is here depicted on the right side for a photovoltaic inverter. And we can do this by performing a so-called fingerprint sweep, or let's say a frequency sweep in general. If we change a single frequent voltage distortion at the clamps at the inverter side or at the converter side, and then measure the multi-frequent current response. Here's a picture of a single-phase inverter. So when we look at it from a white box perspective, we can see basically that we have signal multiplication of the non-ideal DC link voltage, let's say on the left side here in the picture. And then we have the switches that switch at a certain fixed frequency. And then, of course, also we have the control value. And this all leads us to the voltage at the bridge side, which is named U inverter at this paper. And this is what we're going to look at right now. So in literature, we can find an analytic description that is still accurate, even though it's, let's say, from 2003, performed on the double Fourier analysis. And we have marked here in red the challenges. Basically, this analytic description, which is state of the art, still assumes that UDC, even for single phase inverters, is constant, or let's say it's averaged in the analytic description. And also, as we can see, F1, which represents basically the network side and refers to the voltage, is only considering a fundamental frequency that is actually sinusoidal at power frequency. Well, we can say that we all know that in practice this is not really the case, because UDC for one is distorted based on the power flow in single phase inverters that is, let's say, not constant, but interrupted, or let's say circulating, oscillating at twice the power frequency. And of course, our network has a background distortion. All kinds of networks in practice have a background distortion due to other devices that are interconnected. Then we have, of course, the modulation algorithm, and the semiconductors aren't switching ideally. So they're not, let's say, a rectangular switching waveform, or let's say switching form, but they're actually non-ideal. So what we've performed in this study, which brings me to the next step then finally, is we have measurmentally proven that there's actually an interconnection between the harmonic and the superharmonic frequency range we should consider in future studies actually. So we have set up a laboratory test stand that basically consists of a programmable amplifier as a network simulator to be able to actually apply different voltage distortions. We have used a single phase inverter for photovoltaic applications, but the basic setup for these single phase inverters is pretty general. We have used measurement equipment up to 1 megahertz, so we can actually see some things accurately enough in the superharmonic frequency range. And we assumed the measurement uncertainty below 10% for voltage measurements about 50 millivolt and current measurements about 50 milliamperes. So we are actually in a range where we can make assumptions and actually conclude that the measurement results are not based on some uncertainty. So as I mentioned, for the test signal, we apply for one a fundamental frequency, which is 50 hertz in this case, and an amplitude of 230 volt RMS, so 230 volt square root 2. And we have performed the frequency sweep for a single frequent voltage distortion from 60 hertz up to 2 kilohertz, each in 10 steps, while we have not varied the phase angle and the amplitude we have also kept. So down below you can see, let's say, a figurative description, which means on the x-axis we have represented the number of measurements. So we have performed somewhat below 200 measurements for these 10 hertz steps. And the frequency that is excited is up to 2 kilohertz. So we have excited the inverter at the frequency range up to 2 kilohertz, which, as I explained in the beginning, is considered in our case the harmonic frequency range. And on the next slide, we have measured, of course, the frequency range. Here it's depicted on the right side up to 20 kilohertz. So we have applied the frequency sweep, which you can see for each individual measurement. We have changed the excited frequency. So from left to right, you see that the lower rows basically increase in frequency range, which is the excited frequency. But still in the area above or around 60 kilohertz, which is 60 kilohertz is a switching frequency, we can see these parallel lines basically that are frequencies generated by the convolution. So basically we can see that the low frequency range actually mirrors into the high frequency range. So on the left side again, we can see the voltage at the inverter bridge, which we were going to study, and where we saw that the frequency range actually interact between the superharmonics and the harmonics. In practice, we have to admit that this has not been addressed or identified probably because we can see mitigation by the grid side filter circuit. So in general, the filter is able to suppress or to mitigate in many cases these frequency components in practice if we design it correctly. However, we should take care of this for the control, because if the control, let's say, has internal signal processing and also for the analytic description, it would be convenient to have actually accurate description and not just something that makes assumptions about averaging and so on. Which brings me already to the conclusion. So as a summary, we can say we have studied frequency couplings between the harmonic and the superharmonic frequency range. And we can make use of the standard frequency sweep to identify the frequency couplings even in the superharmonic frequency range and not how it is used typically just for the harmonic frequency range. Signal multiplication of the switching signal, the control signal, and the DC link voltage at the inverter bridge leads basically to this coupling of the harmonic and the superharmonic frequency range that has not been addressed to the author's knowledge so far at the moment at all. But however, fortunately in practice so far, the grid side filter can mitigate the frequency coupling in the superharmonic frequency range if designed properly. So when it comes to future work, we need to reconsider and improve our analytic description. And of course, we should consider this frequency coupling in the design process, especially when we're studying superharmonics in future more accurately to guarantee a stable device behavior and other effects in the low voltage networks. So thank you for your attention for now. And of course, I'm happy to answer any questions. Thank you very much.
Thank you very much for your presentation. So we have some time for questions. Any question from the audience? Okay, I have a question, very short, very brief. Can you detail a bit more the signal processing techniques you've used? I mean, did you compare Fourier or wavelet or any other technique?
Yes, this is a Fourier. So we have performed the Fourier analysis to let's say evaluate the time domain measured data in frequency domain. And this is all in a stable operation of the device, so which enables us to just make use of simple DFT.
Did you hear my question, Elias?
Yes, I answered it. Or sorry, can you? I don't know if you can hear my answer. Could you hear my answer?
Can you can answer, please?
Oh, maybe it got lost. So yes, we have used the DFT, so Fourier analysis we have performed on the time domain data that we have measured in the test stand. If this answers the question, or maybe I've misunderstood the question. So we have not made use of wavelets in this study. Does this answer the question?
Final
or
presentation, which is a video, and the title is Power Quality Impact of PV System Integration on Petroleum Development or NAN, PDO, Mina Al-Fahal Distribution Network. The authors are Faisal Al-Harthi, Mohammed Al-Badi, Rashid Al-Abri, and Abdullah Al-Badi. So I think we have a video for this presentation.
Hello everybody, my name is Faisal Harthi, working in Petroleum Development Oman. I would like to thank you for this opportunity to present my papers with International Conference on Renewable Energies and Power Quality 2021. The title of my paper is about power quality impacts of PV system integration on power development Oman. ميناء الفحل distribution networks. It's under Sultan Qaboos University's Department of Electrical and Computer Engineering. The presentation slides outline consists of 6 main topics. First, background, then system data, and after that it's talk about the impact on unbalanced, harmonics, and flickers. Finally, summary and conclusion. The importance of solar photovoltaic system has grown significantly with the continuous development of the solar cells industry over the past years, as shown in the displayed figure in these slides. However, studying the potential impact of the solar PV systems on the distribution network has recently become a significant topic with a high attention. Since then, Oman has continuously worked towards developing its infrastructures in the energy sector to enable a more sustainable future. Furthermore, the country, under the guidance of His Majesty Sultan Haytham bin Tariq, is focusing on developing a creative and diversified economic based on the objective established from Oman Vision 2040 under the environment and natural resources priority. The Oman 2040 vision that was announced on 13th May 2019 stated the Oman Renewable Energy Strategy under the Environment and Natural Resources Performance Indicator that the total renewable energy consumption percentage of the total consumptions to be 20% in 2030 and the range of 35 to 39% in 2040. The Petroleum Development Oman MAF Solar Car Park location has a high level of solar radiation throughout the years. The PDO commissioned Phase 1 and Phase 2 of the Mina Al Fahal Solar Car Park projects in January 2018 and December 2020 respectively. The total project's installed capacity is about 8.8 megawatt peak with a total coverage area of 34,600 meters square. The solar MAF power is used to supply power to PDO offices and buildings. The plant area of Phase 1 and Phase 2 is divided into 5 blocks. The Phase 1 is highlighted in blue color and the Phase 2 is highlighted in the red color. The blue color indicated Beit Al-Bushra area, Beit Mina Al-Fahal's area main, and Beit Mina Al-Fahal overflow area. And the Phase 2 indicated Beit Sahel Malih 1 and Beit Sahel Malih 2, and finally is PDO Training Center HLD. Muscat Electricity Distribution Company MEDC delivers electricity to all residential, industrial, commercial, agriculture, and government area in the Muscat as per the license granted by the Authority of Public Service Regulation APSR. Hence, PDO Mina Al Fahal 33 kV gas insulated substation is connected to MDC network via Al Falaj 132 over 33 kV substation by 420 MVA 132 over 33 kV power transformer rating links to the 33 kV switch board and 33 kV cable feeder Al Falaj 124. PDO MAF 33 kV consisting of 3 transformer 50 over 20 MVA 33 over 11 kV power transformer installed in 33 kV bay links to the 11 kV Mina Al Fahal intact GIS station. The 415 LV substation and the switchboard electricity supply is taken from 2500 kVA 11 kV over 4333 voltage and auxiliary transformer, which are taps from the 11 kV RMUs as shown in the figures. The main objectives of the paper is to study the impact of grid-connected solar PV system voltage unbalance, flickers and harmonics, the measurement of unbalance, flickers and harmonics at PDO solar PV system using Power Network Analyzer, which is installed in the existing solar PV systems for power quality measurement. The voltage balance is the three-phase voltage and currents have the same amplitude and are phase shift by 120 degrees with respect to each other. Unbalanced condition occurs if either or both of these conditions are not met. Unbalance could cause by source structural asymmetry or load imbalance. Unbalance causes negative impacts on equipment such as machines, variable speed drives, lines, transformers, and system distortions. Unbalance can be mitigated by addressing its source or adding unbalance mitigation device like Unified Power Flow Controller UPFC or compensator. These slides present the unbalanced quantification indices. The National Electrical Manufacturers Association NEMA used the line voltage unbalance rate to calculate the unbalance as the ratio between the maximum voltage deviation from the average line voltage magnitudes to the average line voltage magnitudes. The Institute of Electrical and Electronic Engineering IEEE used the same unbalance description with the slight change as the IEEE applies phase voltage instead of line-to-line voltages. The most common definition of unbalanced voltage is the voltage unbalance factor under the International Electrical Commission's IEC, which is known as the voltage components relations of the negative sequence to the positive sequence. Oman Grid and Distribution Code used voltage unbalance factors and should remains below 1% unless the abnormal condition prevail. The result of unbalanced measurement shows that the solar PV system installation had a minor impact on the voltage unbalance as system consists of three-phase inverter. The voltage unbalance was sustained within the standard limits of 1% with and without the solar PV system. The voltage unbalance variation is due to the demand variation. Harmonics levels refer to the quality of sinusoidal waveform for both current and voltage emitted by nonlinear loads, transformers, and usage of power electronic device. Total harmonic distortion is used to quantify harmonic distortion level. The 5% voltage total harmonics limits is according to the IEEE 519/2014, while 2% for the distribution level is the limit of total harmonic distortion according to Oman Grids and Distribution Code. Harmonic measurement results conclude that the voltage total harmonic distortion level is following the daily load profile. Result shows no violation in the voltage total harmonic distortion limit. During the early and late hours of the inverter operation, high level of current total harmonic distortion were observed. This is due to the fundamental current being small during this time. Flicker is known as the impression of understeadiness of visual sensation induced by a light stimulus whose luminance or spectrum fluctuate with the time. Flicker impacts unpleasant feeling like work efficacy, health problem, nausea or headache, epilepsy, seizures, affect sensitive electronic device. Two indices are used to assess the flicker severity. PST is the short-term flicker severity index evaluated over a short period of 10 minutes, and PLT is the long-term flicker severity index evaluated over a long period. It's calculated for 2 hours of the observation period using 12 successive 10 minutes PST values. Oman distribution codes refer to IEC 61037 indicative value for the planning levels of flickers, having 0.9 limits for PST and 0.7 limits for PLT. The fast fluctuation in the solar radiation because of cloud movements may result in considerable variation of the solar PV output power that produce voltage variation at the PV point of common coupling. Flicker measurement result shows that PST and PLT level were within the limit except for few incidences. Infrequent spikes were found during a daytime for both partially and cloudy day as well as without solar PV generation period. The flicker level is due to the different reasons, including network operation, load variation, and solar PV system output variations. Finally, summary and conclusion. The main objective of this work is to study the impacts of PDO-MAF grid-connected solar PV system on distribution system, voltage unbalance, harmonics, and flicker through field measurements. The field measurement revealed that the unbalanced and harmonic distortion levels are within the limits. However, flicker distortion level required further attention as infrequent spikes were recorded, in addition to the passing clouds that result in solar PV system output variation. The flicker levels is affected by network operation and load variation. Worth to mention that the low impacts of the solar PV system on PDO-MAF industrial distribution network is partially attributed to the high short circuit level in the system. Thank you. This is the end of the presentation slides.
Well, thank you very much for your presentation. Well, with this video, we close this A1 session. Sorry, but we have no time for questions. Now it's time for the welcome lunch, and then we will proceed with the visit to the PSA at 3 p.m. Thank you very much.